Molecular orbital theory, chemical bonding, class 11. It was proposed by Hund and Mulliken to explain the paramagnetic behavior of oxygen as well as boron molecule B2, and about the metallic bonding also like Li2, how these bonds are going to exist. The electrons in a molecule are present in various molecular orbitals as the electrons of atoms are present in the various atomic orbitals. Like atomic orbitals only, now the electrons are going to be in the molecular orbitals. Molecular orbitals are formed by linear combination of atomic orbitals, LCAO. Okay, linear combination of atomic orbitals is LCAO of comparable energies and proper symmetry. What is the meaning of this? Comparable energies means 1s can join with 1s, 2s can join with 2s, 1s cannot join with 2s. Okay, proper symmetry means px can join with px, py can join with py, pz can join with pz. That is explained here. You can see this means that 1s orbital can combine with another 1s orbital but not with 2s orbital, because the energy of 2s orbital is higher than that of 1s orbital. Okay, one point is clear. This is true only for homonuclear diatomic molecules, and we are discussing about homonuclear diatomic molecules only in class 11. By convention, z-axis is taken as the molecular axis. Okay, now, so in all your problems, it will be taken as molecular axis, z-axis. Okay, so 2pz orbital of one atom can combine with 2pz other orbital, and that is going to form sigma molecular orbital, but not with the 2px orbital or 2py orbital because of their symmetry. If 2pz orbital is like this, 2px orbital will be like this and 2py will be like this. So they cannot be combined. For example, first atom 2pz orbital is like this, second atom 2py is like this. So they cannot mix. A 2px can join with a 2px. A 2py can join with a 2py. A 2pz can join with a 2pz like this. Molecular orbital is polycentric. That is, an electron in molecular orbital is under the influence of two or more nuclei because that is present in between the two atoms. The number of molecular orbitals formed is equal to the number of combining atomic orbitals. If two orbitals are combining, two orbitals are going to form. When two atomic orbitals combine, two molecular orbitals are formed, right? One is known as bonding molecular orbital, BMO. Another is known as anti-bonding molecular orbital, ABMO. It may be noted that the bonding molecular orbital is stabilized to some extent as the anti-bonding molecular orbital is destabilized. That is, energy lost by BMO is equal to the energy gained by ABMO, but total energy of two molecular orbitals equal to the sum of energy of atomic orbitals. This we can show with one simple diagram. For example, this is one orbital, this is another orbital. They are joining to form one bonding molecular orbital, one anti-bonding molecular orbital. This is ABMO, this is BMO. So if you see this, it is increased energy, this is decreased energy, that will be same, and the average is equals to the regular atomic orbitals. Order of energy of various orbitals is bonding orbitals, non-bonding orbitals, and anti-bonding orbitals. Okay, now this is anti-bonding molecular orbitals, more energy, bonding molecular orbitals, least energy, atomic orbitals, intermediate energy. The molecular orbitals like atomic orbitals are filled in accordance with the Aufbau principle, obeying the Pauli's exclusion principle and the Hund's rule. That means all the rules are to be followed. The molecular orbitals are named as sigma, pi, delta, etc. Formation of molecular orbitals by LCAO method. Okay, linear combination of atomic orbitals. According to wave mechanics, the atomic orbitals can be expressed by wave functions psi, which represent the amplitude of the waves. The atomic orbitals of two hydrogen atoms A and B may be represented by the wave functions psi A and psi B. Mathematically, formation of molecular orbitals may be described as molecular orbital is equals to psi A plus or minus B. If you are taking bonding molecular orbital, that is addition of the wave functions, anti-bonding molecular orbital, is subtraction of the wave functions. Bonding molecular orbital, addition, anti-bonding molecular orbital, subtraction. Quantitatively, the formation of molecular orbitals can be understood in terms of the constructive or destructive interference of the electron waves of the combining atoms. During the formation of BMO, the two electron waves of the bonding atom influence each other due to constructive interference. I think the diagram should be there. If it is not there, I give you the diagram, no problem. It is like this. One more you take. Now, this is bonding molecular orbital, addition of the wave functions, and this is anti-bonding molecular orbital, subtraction of the wave function. This is psi a plus psi b, and this is psi a minus psi b. During the formation of anti-bonding molecular orbitals, the electron waves cancel each other due to destructive interference. Just now I have shown you. The electron density in bonding molecular orbital is located between the nuclei of the bonded atoms. The electron density in anti-bonding molecular orbital is located away from the space between the nuclei, that is nodal plane. The increasing order of relative energies of molecular orbitals having less than or equal to 14 electrons. Sigma 1s, sigma star 1s, sigma 2s, sigma star 2s, pi 2 px, pi 2 py. This y should be small. Then sigma 2 pz, pi star, sigma star 2 pz. For more than 14 electron system, there will be small change in this. The sigma 2 pz will come first, then this one. Rest is same.